Alright, so thermodynamic, boleh faham tak belajar thermodynamic? Can you understand?
Bolehlah sikit-sikit.
Susah sebenarnya online kelas ni. Alright, so baca table boleh buat tak?
Kalau buat dengan Sir boleh. Bila buat sendiri dia macam a bit stuck, ada dapat, ada tak.
Alright,
Confused.
so basically thermodynamics banyak refer table. Okay? Betul kan? You have all the tables up until table starting from table table A2 up until table A7, the compressible regions. Tapi A7 kita jarang pakai lah. So A6 is a superheated, and then A4 is the saturated for temperature, A5 is saturated for pressure. So in thermodynamics you have tables that you're going to use. So same goes nantilah dalam heat transfer. Tapi itulah dia. Kena sentiasa practice. So if it's hard for you to get in touch with PM Zahir, dia quite busy. So you can ask me as well if you don't understand thermodynamics. Okay, sebab this is my background, thermodynamics and heat transfer. So I know both subject lah. Okay, so previously memang saya selalu ajar thermodynamics and also this subject, the combination between the thermodynamics and heat transfer, but for FKE student. Alright, so this is like my first time, and then also this is the first time this subject, okay, this combination subject in FTKEE. Like previously saya rasa they combine I think statics with heat transfer, if I'm not mistaken lah. Betul kan?
Betul.
So
Ya, Puan pernah ajar saya lah.
ya ke?
Masa diploma dulu.
Awak diploma FKM?
FKE.
Saya tak ajar diploma, saya ajar degree FKE.
Ada masa time repeat.
Saya diploma saya tak ajar, saya ajar kalau FKE saya ajar degree je.
Tapi itu ada masa diploma. Bila tak? Puan ajar statik kot.
Saya tak pernah ajar statik, salah orang ni. Amboi, sonok gelakkan orang ya. Alright, so it's already time. So baru 24, saya tak kisahlah, saya proceed je. Okay, so nanti yang the rest akan masuk, dah ada follow je lah. Alright, so right, I don't know, should I speak English or BM? I'm not sure if the guy already in here or not. Otherwise, I can just like, okay, explain in bahasa. It's much more easier for you to understand actually. What is your friend's name? Record tak? Kalau kadang-kadang kena remind saya, kadang saya tak ingat. Apa nama kawan awak tu? The foreigner? Oh, panggil dia Muhammad je. Alright, so Muhammad, are you here? I don't think so. Seems like it's not. Is he here? Seems like it's not. Okay, so alright. Assalamualaikum everyone. Good morning. So this is our first time meeting. Alright, can you like switch on your camera for a while? Just wanted to see your face.
Alamak. Boleh.
Hey, come on. Buka kejap je video. Just want to see your face. Amboi, kelas online lama, rambut pun panjang. Gosok-gosok mata baru bangun tidur lah ni.
Madam.
Yang lain mana? Oh, yang seorang ni dalam bilik gelapnya lah, hai. Bilik gaming ke apa tu?
Bil tak banyak.
Aduh, macam-macam lah korang. Yang lain ni mana? Saya tak kenal. This is like first time meeting and I'm not from FTKEE. So you don't know me, I don't know you. Ni baru habis solat duha ke dengan telekong? Oh, yang lain ni mana ni? Malu tak nak buka. Line problem. Taklah segan, saya nak tengok je muka student saya. Dah lah tak jumpa depan-depan. Ui, siap pakai mask lagi, SOP sangat. The rest, we have Lisa, Asma, Hasif, Haida, Dominic, Azizi, Aiman. Okay lah, yang lain ni macam segan-segan ke apa ni?
Tak mandi lagi kot.
Alah, tak ada siapa bau lah online. Komen-komen diri sendiri je yang bau. Alright, okay. Hai, sibuk nak belajar juga ke si kecil tu? Okay, it's okay. Thank you. Yang the rest tu tak apalah, mungkin segan, tak mandi ataupun dah tidur. Alright. So, before we start, thank you. Okay, so before we start, okay, I prefer to use Ulearn as a main platform. So all the lecture notes, tutorial discussions, your tests, okay, lab report submissions, everything will be submitted. Okay, you have to submit. You have to check Ulearn regularly. Okay, especially the attendance. Every time we have class, lecture class, also the tutorial sessions, then you have to record, self-record. Okay, yourself for the attendance, and I will use that as the evidence. Okay, untuk nanti bila last tu, okay, nak kena check all the attendance record students. Okay, so I will be based on the Ulearn attendance. Okay, so I'm going to share the Ulearn for a while. So this is how the Ulearn look like. Okay, semua dah familiar lah kan? You are year 2 already. So today attendance, okay, so the lecture class, the durations, okay, is only from 8 to 10 AM, okay, based on your timetable. So waktu attendance tu boleh buka ataupun you can access to record your attendance is between 8 to 10 AM. So for lab sessions, okay, depend on your sections. So for S12 will be on Wednesday, right? Wednesday, yeah. Wednesday. And then for the other sessions, hari apa ya kelas? Section S11. Lab sessions hari apa? Selasa what time? Selasa pukul berapa start?
10.
Pukul 10 jugalah. So hari Selasa. So you supposed to your lab sepatutnya dengan Mr. Itaen, but he seems so busy, so dia tak commit lah to teach. So nanti kalau nak kena evaluate on him, you can like jujur je lah evaluate. I guess masa thermodynamics, all the tutorial and also the lab sessions conducted by PM Zahir. So same goes for the heat transfer section as well lah. So I will give all the instructions and everything. Okay. All right. And then back to this. So now we are in week 7, but then because I already prepared everything earlier, so supposedly we're going to start heat transfer next week, but because next week we have tests during the class hour. So we're going to start the test at 8:30, okay, in ULearn. So this is we're going to cover this chapter today. So basically this is like introduction chapters, and then we have a conduction chapter, convections, and then natural convections, and then boiling and condensations. The last week, okay, PM Zahir nak ambil to do revision week for thermodynamics. And then I have this one, okay, heat transfer tutorial. So setiap kali, every time we finish completed one chapter, you're going to answer tutorials. So all the questions here in the tutorial sheets, and then I created this forum. So you just simply like click the tutorial heat transfer here, and then just click the add new discussion topic, and then write down what is the question number. So let's say you are answering question 1, so you just like Q1, okay, and then you can write it down here, or you can post your file, upload your file in here, and then post to forum. And then we're going to discuss, and I'm going to reply based on your solutions, everything in this forum. That's why I ask you to check the ULearn regularly, especially for the tutorial part. Okay, I hope everything is clear. And then for the lab, okay, yeah, the lab, I have uploaded all the 3 labs that you're going to do in heat transfer. So you have the conduction, convections, and radiations. So all these 3 labs actually, it's a simulation lab. Okay, I provide the link for you to do the experiments. So, but then if you have like face-to-face sessions, then lab ni semua tak ada dekat UTM lah, okay, tak ada dekat FTKMP. Alright, but this is a very nice simulation, so that you can play around and see what happens if you increase the diameter, if you reduce the thickness, and so on, and if you change the materials and everything. So you can notice, is it make any changes and so ever. So you can play around, okay, instead of just follow the lab sheets what you have to do. And then you can, if you have like extra times, okay, so you can just like, okay, try and error if you change it to these and these. Okay, so lab sessions akan start minggu depan for both. So S11 will start on Tuesday, Selasa, okay, and then for S12 on Wednesday. So do the first lab, the conduction lab, okay, and then you have 1 week to submit your report. So I've created these lab report submissions, but then this is only for S12, and then later I will create lab report submissions for S11. Okay, so everyone clear?
Clear.
Alright, so we're going to start with the first lecture. Okay, so this is our first lecture. Basically, semua subjek. For the first chapter is like the introductions, the pengenalan lah to this subject. Alright, so basically what are you going to learn, okay, in this chapter is the general introductions. Okay, what is heat transfer? What is the heat flux? Okay, and then you have the three modes of heat transfer. We have the conductions, convections, and radiations. So this is the objectives. Okay, you can read by yourself. So I'm sure you all of you familiar with this infographic slide here. Am I right? Okay, and definitely PM Zahir, okay, already explained this thermodynamic application. So I'm going to skip this. So let's focus on heat transfer. All right, so we have heat transfer, we have thermodynamic, we have heat transfer. So what is the difference between these two subjects, okay? Let's say, okay, so we have this setup, okay? Let's say we have this setup, we have the steel bar, okay, and the temperature of the steel bar is 25, and then we place the steel bar inside a hot water. Okay, the temperature of the water 100 Celsius. So in thermodynamic, what your interest is, you want to know what is the equilibrium temperature at the end of the state. Okay, so like this. So the initial states, you have two different temperatures, and then at certain time until the last state, and then you reach the T equilibrium, the temperature equilibrium states. Okay, so you just want to know what is the equilibrium temperature. But for heat transfer, okay, you're going to predict the temperature distributions. Okay, so you're going to you will be able to know the temperature of the water and also the bar, okay, with respect to the time. Meaning that, okay, initial states, okay, the temperature of the water is 100 and then the still bar is 25. Okay, after 1 hour, you notice that the water reduced to 80 Celsius and then the still bar to T Celsius. And then after reach the equilibrium states, okay, let's say 2 hours after that, okay, you reach the equilibrium state. The temperature of both are 35 Celsius. So what can we say that thermodynamics is actually you just concerned about the amount of heat. So the heat in thermodynamics is the work and heat. Okay, heat is energy actually. It's like amount of energy. So the energy can split into heat and work. So that is thermodynamics. Okay, and for heat transfer, it helps you to predict temperature distributions, okay, and also to determine rate of heat transfer, okay, across the surface due to the temperature gradient. So what is temperature gradient and everything? Later, okay, kita akan tengok lah. And then in heat transfer, we have cases, steady state cases and also unsteady state. Normally, we call it as a transient heat. This one, okay, transient heat transfer. So steady state, okay, this is like common term. Will we cover heating critical point? What is that? Before a material breakup? That is for which chapter, Hasif? Okay, I'm not sure what you mean by critical point.
Because if heat transfer through a material like a steel bar, there is a certain limit which at one time the steel will totally burn or break up.
Oh no, not until that, until the failure, right?
Yeah.
So no, we not cover up until that.
Okay.
Alright, just want to know what is the rate of heat transfer.
Okay.
Have you learned before heat transfer?
No, but I'm interested in knowing.
Normally, actually heat transfer dia tak akan buat material breakup actually. Okay. Biasa kalau I'm not really sure what you mean by breakup. Is it like patah ke?
Something like that. Because
Okay. So normally, if you mean like that, biasanya heat transfer dia tak akan effect sampai boleh patah macam tu. Normally yang tu is more to solid structure. Okay, so solid you have like the impact test or the hardness, the testing. Okay, the hardness, and then you have what impact, hardness, tensile, everything. So that one, dia bila dia sampai the critical point, then it will break up. But heat transfer tak ada. Okay.
okay.
Alright, so okay, so we go back to the steady state. So steady state ni bila kita sebut, when we talk about steady state, okay, we know that all the properties does not change with time. So in our case, because we deal with heat transfer, we deal with the rate of heat transfer. So 5 kilojoule per second, okay, or kilowatts, 5 kilowatts, this is rate of heat transfer, okay. So doesn't matter if it takes only 1 second or 5 seconds or 10 seconds, we only concern the amount, okay, the value, the amount of rate being transferred. Okay, so in this case, let's say kat situ dia bagi apa 5 kilowatts, so that is only our concern, 5 kilowatts. So for the case of unsteady state or transients, okay, the rate of heat transfer will change, okay, depending on the time. So for this case, let's say for 1 second, okay, the rate of heat transfer is 5 kilowatts, and then for 5 seconds, the rate becomes 10 kilowatts. So it's changed, but for degree level, we're going to focus only for case steady state. All right. So this is the theory as well. And then we say heat. All right. So heat actually is one type of energy. Okay. Sometimes when people say, okay, the energy transfer, so automatically it is heat transfer. Okay. So, but it can be also chemical energy. So it can be what again? A lot of energy. Okay, so we have like potentials, kinetic, mechanical, magnetic, nuclear energy, electrical energy. Okay, a lot of energy. Okay, so actually heat transfer ni, okay, why electric? You are electric students, right? Okay, why electric student? Okay, need to learn heat transfer. Okay, because it applies in many areas. Okay, the knowledge of heat transfer. So when you want to design cooling systems for motor generators and transformers, you're going to apply heat transfer knowledge. And then you want to construct them or refrigerations, air conditioning systems, you want the thermal power plants, everything involve heat transfer. So that's why it is important for all engineering students to learn, okay, at least to know a basic knowledge of heat transfer. Okay, so this is some of the applications. So our body, okay, we generate heat. Okay, so that is part of heat transfer as well. And then because we have the surrounding air that cool our body, okay, so that is concepts of heat transfer. And then we have the air conditioning, all the electronics equipments, the power plants, and so on. All right, so before we go to the modes of heat transfer, okay, let's recall back. And then this is like most common variables or properties used in thermodynamic as well as in heat transfer. So we have internal energy and enthalpy. All right. So let's say we have two conditions of fluids. The first one is the stationary. Okay. As you can see here, we have the stationary fluids. Maknanya that liquids, okay, duduk dekat kita letak dalam vessel, okay, ataupun tank. And then another one, we have a flowing fluid. So the energy for the stationary fluids is equals to U. What is U? Okay, it's similar to thermodynamics. Okay, U is the internal energy. Okay, so the U value normally in thermodynamics, you can just simply pick from the table. Alright. So, or you can calculate as well. Okay, so U internal energy. What is internal energy? Anyone? Ingat tak? Dalam
Energy yang dah sedia ada.
again, Khadira?
Energy yang dah sedia ada.
Ya, itu dia punya expression. So, it's okay, it's okay. Okay, so internet
Chemical energy.
again?
Chemical
No.
energy.
No. Okay, internal energy is actually, okay, I know it's kind of difficult for electrical students nak belajar all the mechanical stuff. Okay, sebab saya ajar sebelum ni pun, okay, diorang macam tercengang-tercengang, but it's okay. Alright, so internal energy is actually, it's a combination of microscopic energy. Remember, you have the microscopic and macroscopic energy when you learn in thermodynamics. So what is microscopic energy? You have the kinetic and potential. Okay, so for this case, the U here, which is your internal energy, okay, it's a combination between potential energy and kinetic energy. Okay, alright, so let's say for the case of fluids, okay, the energy is equals to H, the enthalpy. Okay, so how do you calculate, how do you determine the enthalpy? For thermodynamics, you have table that you can choose your value. Okay, but you can calculate as well. So you can use these equations where enthalpy is actually equals to the internal energy plus with the flow work. Okay, this is the PV here represents the flow work because we have a flowing fluids. So automatically dia ada kerja. They have work. Okay. So remember thermodynamics, you have heat and you have work. So the heat represents by the internal energy, and then the work represents by this PV, the flow work. Alright. And then next we have the specific heat. Okay. And then we have two specific heats, which is the CV and CP. So this is a specific heat at constant volume, and then CP at a constant pressure. So this is also from table, and same goes for heat transfer. And then from this CP and CV, you can calculate for the R constants. Okay, where do you use the R constants is for the ideal gas. Okay, so R is, come, I write it down. Oops. Okay, so you have the, okay, how do you want to determine the R? Where's my pen? Okay, so R is equals to CP minus CV. Where do you use this R? For the ideal gas, where you have the equation PV mRT. So this R is this. Okay? Alright. And then we have the energy transfer. So energy here is the heat and also work. Okay? So what is heat transfer? So heat transfer is this one. The symbols, normally heat transfer rate, the symbol is Q dot. This one. Okay? And then we have another one, which is heat flux. So heat flux, the symbols will be Q. Sometimes, okay, they use Q, small q dot, or they use like Q prime prime that represents heat flux. Okay, if you refer to different books, okay, from different author, they use different kind of symbols. So the symbols is actually like a dummy. Okay, so but in order to not to make student confused, it's better to know that heat transfer rate, okay, if The question asks you find heat transfer rate, find the rate of heat loss and everything. So that will be this Q dot. Okay, and then if the question asks you to find heat flux, then you will use the small q. Okay, so what is heat flux? So heat flux is the rate, okay, of heat transfer per unit area. So this is the equations for the heat flux. Okay, and then the Q here is what? This is the energy transfer. You just want to know what is the amount. That's why the unit is joules. Okay. The rate of heat transfer, the unit must be watt or joule per second. Alright. Can you follow? Alright. Okay, so and then we have power. Kalau electrical students, they normally involve power. You have the voltage and the current. Okay, you just multiply both, so you get power, right? So power is actually similar to this heat transfer rate, Q dot. Okay, so the unit is still watt. Okay, alright. So this is all the theories. And then we're going to take a look at the modes of heat transfer. So we have three: conductions, convections, and radiations. So how are you going to distinguish these three modes? Alright, so basically kalau untuk for the conductions, okay, it involves a solid substance. Okay, that will be the medium for conductions. Okay, so let's say I have like a metal bar and then I'm going to heat up at one end, and later I notice I can feel the heat, okay, become hot at the other side. So that is conductions, okay, it transfer the heat through solid. And then convections, okay, it must involve fluid motions. Okay, fluids dekat sini, okay, it can be liquid, it can be gases. Okay, so that's why we call it as a fluid. It's not necessarily liquid. Okay, so for convections, we have free convections, and also we have forced convection. So examples, let's say I have like a hot tea. Okay, I have a hot tea and then I put it on the table, and then after 1 hour, okay, I notice that the tea no longer hot. Okay, all right. So what makes it cool? Okay, it because of the convections. Because bila saya letak hot tea tadi dekat, saya biarkan dekat atas table, we have the air surrounding. Okay, so the air ni dia moving. Okay, but we can't really see lah what is the pattern dia punya moving and everything. But people already do investigate, and for the natural, they tend to move in circulations. Okay, so as you can see in the diagram here, kat sini kan, you nampak dia ada oven, and then kat luar, biasanya kalau kita masak, let's say lah furnace, kat luar-luar ni pun panas. Okay, kita rasa the heat. Okay, and because we have the air surrounding, so this is like natural convection. So it tends to circulate. Okay, so that is convections. And then radiations, of course lah, the easiest examples, we have the sun. Okay, lepas tu dia punya cahaya, the sun lights to, okay, strike to the earth, okay, that is by radiations. Okay, so for the radiations, okay, dia boleh go through between surfaces, gas, and also vacuum. So let's take a look at the first modes, which is conductions. So when we say conduction, automatically we know that we need to use a Fourier law. Okay, so this one, the Fourier law of conductions, and this is the equations. Okay, so this is actually Q dot. Okay, this is all Q dot because I want to make it standardized. Okay, this is all the Q dot. Rate of heat transfer. Okay, so this is the rate of heat transfer by conductions. Okay, Fourier law equation. So this is the equation: negative Ka, Okay, and this is what we call temperature gradient. Temperature gradient. Okay, and then what is K? The K here. K is thermal conductivity. Okay, we have tables for K value for various substances. Okay, so let's say the metal here, our solid is pure copper. Okay, so our K is 386, and then the unit will be watt per meter Kelvin, or it can be watt per meter Celsius. Doesn't matter. Okay, it's still the same. Okay, no worries. You don't have to change the temperature Celsius to Kelvin, Kelvin to Celsius. Tak perlu. Okay, for the case conductions, you don't have to change the temperature because you're dealing with temperature difference. So if you change to Kelvin, you will get the same value. If you remain the same as Celsius, you will get the same values of temperature difference. Okay. And then let's take a look at this is like theory. I'm not going to touch on that. So we're going to see this one. Okay. So this is the Fourier law equations. This one. Okay. And then we know the K. Okay. What is the materials, the substance for the solid. A is the area. And then this is our temperature gradient. dt over dx. Okay. Let's say you have a plate, okay? Let's say you have like a plate, okay? This is like a plate, okay? And then you know that this side having higher temperature and the front side is low temperature. Okay, you have to remember that heat flows, okay, from high temperature to low temperature. Dia takkan pergi opposite way, okay, daripada low pergi ke high, tak ada, okay. It will not happen. Biasanya daripada high temperature, it will travel to the low temperature regions, okay. And that is the directions of the heat transfer. Okay, that will be the directions of the Q dot. Okay, so because of we have this, okay, we have this is the high, this is the lowest, and then we have this temperature distributions here, or the temperature gradient here. Okay, this graph actually negative kan? Kalau kita tengok linear graph, kalau graph macam ni, wow, no wonder lah sengit. Okay, so if we have like, oh Allah, sengit bengitnya. Susah tau, left-handed. Okay, so we have, sengit bengit nak lukis paksi pun. Alright, so let's say lah, okay, we have this. Okay, kalau graph linear, positif macam ni kan? Alright, okay, so kalau, tapi sekarang ni, let's say this is our axis. Okay, kita punya linear sekarang negatif. Okay, tapi dia follow positive direction. Let's say our coordinate kat sini. Okay, this is y, this is x. Okay, kita tahu dia punya arah Q dot kita, arah follow the same directions as x. Okay, so kita tahu direction dia akan jadi positive. Okay, so the negative sign yang dekat depan ni menunjukkan apa? Nak menunjukkan yang memang kita perlu dapat the negative linear, okay? And then the directions following the x directions. So our value for the Q conductions become Q, or is it in the next slides? Yeah, Q, okay, yang ni lah, malah nak tulis. So we have this, okay? So we have the T1 minus T2. Okay, so your equation, macam mana dekat sini the negative signs already gone, okay, because of this explanation just now. The negative sign just showing you the direction, okay. So equations for the conductions that you are going to use is this one. Okay, Q dot. Okay, yang ni nak tulis ke tak nak tulis? Terpulang lah. Okay, so you have the KA because I notice bila ada K je, I know that you are using conduction. Okay, KA, T1 minus T2 and then delta X. Delta X is the thickness of the plate. Okay, and then the A will be, kalau kat sini kan gambar dia macam ni lah 3D. So the area of this plate will be this A. Okay, let's say dia tak beri area, doesn't even mention anything about the area, length is not given, the width whatsoever. Okay, then how you want to calculate for the rate of heat transfer? You can use heat flux. Okay, remember that the heat flux Q is equals to Q dot over area. Okay, so your Q dot, mana lagi saya nak tulis? Sekejap, saya tambah space lah. Okay. So, you have the Q is Q dot over area. And then, what is your Q equation just now? You have KA T1 minus T2 divided by L, the length, divided by the area, this one. Okay. So, you can just simply cancel out. So, your Q for the heat flux for the conductions will be K T1 minus T2 over L. Okay, why I use L? Why not use X? Okay, so yang actually the real thing is you cannot use X because sometimes, okay, kalau for the case of cylinder, okay, you mana ada length, you mana ada, you normally kita pakai radius, okay. So this one, L is actually the LC, characteristic length. It depends on what types of, what is the shapes. Okay, is it plate, is it cylinder, is it sphere? Okay, tapi biasa kalau untuk conduction, contoh yang kita senang bagi is plate. That's why we use X, okay, to represent the thickness. Okay, so you want to use X, you want to use L, it's up to you. As long as you know that will be the thickness. Okay. So this is how they determine the K value. Okay, they do this setup. Okay. So you have this electric heater, and then of course we need to have like power supply here. So the power supply here, let's say like 200 watts. That is the Q dot. Okay. So sebab kita ada the voltage and the current, okay, multiply both so we can get power. So it's similar to rate of heat transfer. And then we're going to insulate the rest, and then one side will be open to the surrounding. And then we're going to change this white box in the middle here is our materials. We're going to change. Okay, let's say try with diamond. And then we get the temperature here, and then the temperature the other side. We know our Q dot, we know the thickness, so that we can calculate the K value. Alright, so this is how they obtain all these K values. Okay. So you have to remember, lagi besar, okay, the highest the K value, the more conduct, okay, the material is more conduct, okay, it's a good conductor materials, okay. Lowest K, it's more to insulation material, or it can be gases. So this is the range, okay, for the K, for different substances. So the highest is this one. Right. Okay. So the diamond graphite, that will be the highest K value. So ni yang paling bagus conductor material, is the good conductor materials. Okay. And the lowest, tengoklah kat sini dah air, gas, meaning that gases lah. Okay, all these gases, and also insulators materials, they're having the lowest K value. Alright, so this is basically how they deliver the heat. Okay, for solid, of course, because we have cloud of electron, so it's due to the vibration. So from one molecules it transfer to other molecules, and then that's why they can bring the heats from one side to the other side. And then liquid, because of the collisions and diffusion. Same goes for the gas. All right, and then we have the thermal diffusivity. Okay, so this is the equations. We rarely use this actually, but it's just for your information. So we have this alpha, okay, and then we have the heat conductions, which is our K, divided by the heat capacity, the rho and Cp. So rho Cp you can get from table, same goes with the K. So you know everything, you can calculate for the thermal diffusivity. This one, normally for the diffusivity, you will use a lot in mass transfer, which we will not cover that topic. Alright, so next we go to the convection. So convections, we have free and force. And when we talk about convections, okay, we have to use Newton law of cooling. So this is the equations, okay, and again this is Q dot. All right, so Q dot equals to H. What is H? That is convection coefficients. Okay, sometimes we just call it coefficients and people know that that is H. A is the area, okay, and then we have the temperature wall minus the temperature infinity. That the temperature infinity is actually the surrounding air, okay. So this is the equations that you're going to use. And how do you get this H value? Okay, it depends on the properties of the fluids and also the velocity of the fluids. So you have tables to determine H value. So this is example of the table. Okay, this one down here. So for the free convections, let's say we have vertical plate and then the surrounding is air. Then your H value will be 4.5 and the unit is watts per meter squared Kelvin, or the unit can be watt per meter squared Celsius. Okay, for the case convection, it's similar to conduction. You don't have to change to do conversion, the temperature conversion. You don't have to do for convections and conduction. Okay, so kalau dia bagi H di dalam K and then all the temperature in Celsius, you can just simply straight away do the calculations without do the conversions. Okay, so if you are unsure, then if you want to do the conversion, it's still the same. You still get the same rate of heat transfer. All right, and then convections. We have a velocity profile and also temperature profile. So we have a hot block. This is our block. Okay, and then this surface is exposed to the air. Okay, this is a very hot surface and then it is exposed to air. So concept of fluids, okay, the one that near to the surface, the velocity will be at a rest, meaning that the velocity is zero. Okay, so that's why the velocity diagram here, it starts from here, it is zero. As it go further, okay, the velocity increasing. So it's opposite with the temperature profile. So temperature profile, the one that touches, okay, the air that near the hot surface, the temperature is very high, the highest. And then as it go further, the temperature is decreasing. Okay, that's how you plot. If the question asks you, please draw the velocity and temperature profile for convections. Okay, so this is case for natural convections. Okay, so this is a forced and natural. So what makes it different? So natural, okay, let's say I just like go outside, standing outside, okay, and then that will be natural convections. Okay, let's say now it's rainy, Okay, of course, outside temperature, the surrounding temperature is cool compared to my body because my body generates heat. So let's say I just go there and then I just stand there. Okay, and I feel the chilling effects. So that is natural convections. Okay, same goes if you have these hot eggs and then you put it on the table and then after 5 minutes, okay, telur dah sejuk. Okay, that is because of the natural convections. Forced convections, okay, you must have external sources. Okay, or external fan, you have pump, okay, to help increase the velocity of the fluids. Okay, for the forced convections, the rate of heat transfer normally higher compared to natural convections. All right, so this is the equations, and then I think I already explained this. Okay, so basically, please remember if you deal with convections, then you have to use these equations. All right. So, and during the finals and everything, normally the H value will be given. Okay, this is given lah. It's kind of hard and difficult for you to get what is the exact H value. Okay, as you can see here, okay, you gonna consider, is it free convection, is it forced convections, and then if it is gases, then the value ranging from 2 to 25. Let's say if it is liquid, then the value is 50 up until 20,000. So dia ada ranging. It's kind of difficult. Bila ada ranging, you kena tengok pula. Is it what is the geometry? Is it plate? Is it sphere? Is it cylinder? Okay. So banyak benda nak kena tengok lah. And then the last mode, that will be radiations. So radiations, we have two cases. We have the black body and then we have the gray body. So in our level, we focus on the black body only. So this is the equations, the Q emits for the black body. Okay, but this is just to find, this is just to find the maximum Q emit. Okay, so what is the emit? Pancar. Okay, yang terpancar dari black body. Then you have to use these equations. Okay, so we're not going to touch this one. Okay. So this is all the theories about radiations. I'm not going to read one by one. Okay. So let's just focus on this. So we have the Q emit just now for the black body. Okay. So this is the equations, the maximums. Okay. And actually we have emissivity in front here. So because of black body, the emissivity for the black body is actually equals to 1. So that's why they didn't include this. Okay, because any numbers you times with 1, you will get the same values. So you have sigma. What is sigma? Sigma is the constant, Stephen-Boltzmann constant. Okay, so how do I remember the value of the Stephen-Boltzmann constant is 5678. Okay, 5.67 times 10 power negative 8. Okay. So this one. Okay, that is the Stephen-Boltzmann constant. And then the AS is the area of the surface. And then this is the temperature of the surface. Why? Because we have black body. Black body ni, matahari of course not the black body. So black body ni normally kalau kita ada plate. Okay, so we have plate. Then itulah kita punya black body. Alright. Kita ada area dan juga kita ada the temperature surface. So this is the table for emissivity value. Okay, the emissivity is the epsilons. Okay, so for various materials, so black paint, okay, close to 1, 0.98. So white, okay, rendah, okay, lagi cerah, lagi terang, which is like as you can see, the aluminium foil, it's only 0.07. Sebab dia hancarkan balik the aluminium foil, right? Okay. So next, we have the absorptivity. So absorptivity ni berapa ratio? That is a ratio actually. Penyerapan. Okay, the absorbs. Okay, let's say that's why bila panas, okay, avoid wearing black shirts because it will absorb the heat, the radiation heats, and that's why you feel hotter. Okay, so you have the Q incidence. So the thing that, let's say you have the sun, okay, and pancaran dia tu, that is the Q incidence. And then let's say I'm wearing black shirts outside, so I'm going to absorb some of the radiation heat, and then the rest will be reflected. Okay, so this is the equations. And what we call this equation is the Kirchhoff's law. And then the value of the absorptivity, which is the alpha, okay, it's ranging between 0 to 1 only. Okay, so and then you notice here, the keyword here, black body, it absorbs 100%, meaning the alpha is equals to 1. Okay, black body. So this is also theories, and then the equations, the proper equations that you need to use to solve radiations is this one. Okay, kita akan guna ni, equation ni untuk calculate for radiations. Okay, heat transfer by radiations, emissivity, sigma, area, and then we have the temperature, surface, power of 4 minus temperature surrounding, power of 4. For case radiations, the temperature must be in Kelvin. This must be in Kelvin. Okay, you cannot use Celsius, and then you will get wrong answer. You have to use Kelvin. Okay, because of this Stephen Boltzmann constants. All right, so in reality, actually we deal with all the three modes. Okay, but then it's difficult for us to analyze. Okay, so then we reduce it to single modes. Okay, whether it is only the conductions, the convection itself, or radiations, or it can be a combinations. So for example here, let's say we have a combinations between radiations and convections. So this is the Q total equations, the combinations rate of heat transfer equations. Okay, so we have this H combined. Okay, and then we know for these examples we have radiations and convection. So our Q total is actually a combination between convections and radiations. Okay, so what is the convection equation? This is the convection equations. Okay, radiations. This is the radiations. Okay, radiations. And then this is the convection. And then we have this equation just now. Okay, we have this Q total. All right, so if you rearrange this, okay, you replace the Q total here with this, okay, then you notice that you have the H combined, H convections, and then the epsilon, sigma, and then you have the area, everything got area. Okay, so you can cancel out the area term, right? H combined is what you want to know. And then you notice that you have, this is infinite is surrounding actually, okay? You have the S minus T surrounding. This is also you have the S surrounding. This also you have the S surrounding. So you can cancel out this term as well. Okay, so this is left 3. Okay? So rearrange back, then you get your H combination is actually, you left with H convections because this is cancel out. You have this H convections and you have this with the back here except the A. Okay, So you have H convection, H radiation. So H convections, this one. H untuk radiations is the epsilon infinity, and then this is the power 3 just now. Okay. So using this equation, you can calculate for the H combined. Okay, that is the coefficients. Okay, the combined coefficients. Okay, so this is examples for simultaneous heat transfer mechanisms. So for one case, let's say, okay, you have the opaque solid here. So of course, it is a solid, so we have a conductions. And then let's say if through vacuums, okay, it can only happen radiations. That is one mode. Okay, for the two modes, okay, it can be radiations with convections or radiations with conductions. So if you dealing with solid for two modes, okay, if you're dealing with solid, you will deal with radiation conductions. But let's say you have a fluid motions, then you will be radiations and convection. That is the combination. All right. So let's recall back. This is like all the dimensions and everything for the conduction, convections, and radiation. So this is our, okay, make some adjustments. Everything here is Q dot. Okay, so this is also the Q. Okay, that is Q emitted. Okay, that is not rate of heat transfer. Okay, so Q, the rate of heat transfer for radiations. Okay, it's better to write like this. Q dot radiation equals to emissivity sigma area S Ts power 4 T surrounding power 4. Okay, so we have the Fourier law. Okay, so the dt ni apa? T1 tolak T2. So the negative sign is gone. Okay, and then this is Newton law of cooling, and then this is the Q radiations. All right, so let's take a look at examples. So we have 4 examples. The example 1 is the conduction through copper plates. Okay, so we have a plate with 3 centimeter thickness, and then the temperature is 400 and 100. Okay, and asks you to find the Q dot. Okay, the given the K value for the copper, which is 370 watt per meter Celsius. All right, so how are we going to solve this? Okay, using the Fourier law equation just now. Okay, everything is there. Everything is given. Okay, so what is your Q? What's that? Okay, so your Q dot is equals, what is the K just now? It's a 370, and then your area, okay, is not mentioned. Okay, the area there is not mentioned. All right, so if there is no area, okay, you cannot use this. Okay, because area is not provided, then you have to solve using heat flux. Okay, you have the Q, which is the Q dot over area. Okay, so now what is the Q dot just now? Is K with dt x. So the K is 370, temperature 400 minus 100, and then the thickness is 3 cm, 0.03. Okay, and calculate this, you get the answer is 3.7 megawatts per meter squared. All right, can you follow? Okay tak? Boleh faham tak?
A little fast, but okay, insyaAllah.
Laju ke? Am I too fast?
Quite fast, like train, like MRT.
Okay. All right. So, and then we have the convections. So convections, okay, they mesti ada fluid motions. Okay, and then it's given the area which is 50 by 75. And then you have the surrounding temperature, which is 20 Celsius. And then you have the plate temperature, 250. The convection heat transfer coefficients given 25 asks you to calculate the heat transfer. So you just use the Newton law of cooling. Okay. So this is the Q dot. Okay. HATS minus T infinite. So if it is kind of difficult for you to understand the questions, you can do a sketch. So basically, the example 2, the sketch is something like this. You have a hot plate here, 50 by 75, and then the surface temperature is 250, and then you have the temperature air 20, and then you have the H, okay, which is 25. So you know all the values for each variables. So calculate, then you get your rate of heat transfer by convection is 2.156 kilowatt. All right, so example 3 is the radiations. Okay, you have two black plates, okay, 800 and 300. So they exchange heat by radiations. Okay, and I ask you to find the heat transfer per unit area. See, it's already mentioned heat per unit area, meaning that it is Q, the heat flux. Okay. So you have two plates, one 800 and another one is 300. So you're going to use the radiations equations. And then because the question already asks you to find the heat flux, then you have to use the Q dot, the heat flux equations, where you can just simply cancel out the area in the equations. So because it is black body, emissivity is equals to 1. So the sigma is the Stephen-Boltzmann constant, 5.67 times 10⁸ is the sigma. Okay, so this is the highest temperature, okay, the T highest, okay, and then D will be the T lowest. All right, so you get your heat flux, okay, for the radiation case is 69 kilowatts per meter squared. So from this, the radiate ke plate bawah. Okay. So sebab apa kita tahu 800 duduk atas dan area the radiation ke bawah? Because kena ingat heat akan heat being transferred from high temperature region to low temperature regions. Okay, that's why kita boleh tahulah 800 yang akan dissipates the heat to the lowest temperature plate. And then the next example is for the mix. We have the multi-mode heat transfer. Okay, so let's say we use the example 2. Okay, now we have the carbon steel. Okay, the surface, the plate just now doesn't mention what substance. So for the example 4, we know that the plate is carbon steel with thickness 2 centimeter, and then it's mentioned that it lost 300 watt. Okay, so this is Q. Okay, because the unit is watt. Okay, that is the heat loss. And then from plate, surface by radiations. Okay, dia suruh cari apa ni? Calculate the inside plate temperature. Alright, and then bagi the K value. So how are you going to do? Example 2, convection. So convections, okay, you need to mix with what? Okay, you're going to mix with radiations because you have the radiation loss. Okay, convection tadi, they involve fluid flowing. And then dia bagi tahu dah ada radiation loss. Okay, so radiation loss, convection, it's a good combination. And then dia suruh cari temperature plate. Okay, so temperature plate, bila kita nak cari untuk plate solid, so automatically we deal with conduction. So this is the energy conservation. Kita tahulah total of energy in will be equals to the energy out. So temperature here At the top surface, 250. Okay, so the question asks you to find the bottom temperature. Of course, the bottom temperature must be higher than the top temperature. Why is that? Because the heat, for this case, okay, this is the losses, okay? Okay, losses to the radiations. And then we have the cooling also here. So, of course, we know that our heat being transferred from bottom go to up. Okay, this is our Q dot directions. Okay, so that's why kita tahu T bottom ni, dia punya temperature must be higher than T surface because the temperature gradient akan jadi macam ni. Okay, this is T highest, this is a bit lower. Okay, so we have the conductions and then because this is our inlet. Okay, this is our inlet. Macam mana bottom ni boleh tinggi? Dia mesti ada something that supply heat to this surface. Okay, so that will be in energy in kita for this entire systems. Okay, so the convections and also the radiations is our output because it starts to cool the plate. Okay, so this is will be the out. Okay, so we know the conductions, we have the Fourier law. Okay, and then convections, we have the Newton law, and then radiations is given already. It said it lost by radiation 300 watt. Okay, so just take 300 for the radiations. And then you're going to calculate everything. K is given. Okay, this is from example 2. What is the value? In example 2, 2.156. Okay, so this is 2.156 kilowatt. Okay, or 2156 watt because this is 300 watt. Okay, so you need to find the T bottom. You know all this. So rearrange that, calculate, and then you get your T bottom temperature is 253 Celsius. Okay, boleh faham tak example 4 ni? Alright. Okay, so next. Example as well. Okay, so we have a logic chip. Okay, it dissipates 3 watts. Okay, so maknanya bila dia dissipates, okay, kat sini, that is our Q dot. Okay, the amount he dissipated in 8 hours. Okay, and then the area is given. Alright, so for this kind of examples, okay, it gives you time. So bila bagi time, macam slide yang energy transfer tadi, okay, you have the Q, which is the amount of energy, okay, is equals to the rate of heat transfer times with time. Okay, so in this case, we know that the Q dot is 3 watts, and then what is the time? Is 8 hours. And then you just multiply, and then you get 24 watt hours. Normally kalau kita electricity ke whatsoever, kita pakai kilowatt hour, right? So you have to change the units to kilowatt hour. So it becomes 0.024 kilowatts hour. Okay, that is the amount of heat that this logic chip use. Okay, and then because it's given the area, okay, which is in inches. So you have the heat flux, Q is equal to Q dot over with the area. So you get 3 watts divided by 0.08 inches squared. So your final heat flux for this logic chip is 37.5 watt per inches squared. Okay, so contoh ni dia pakai inches. Okay, sebab dalam equation lain tak ada yang involve dengan tak ada yang pakai unit meter. So you can just use the inch unit. Okay, kalau let's say dia suruh calculate dulu the Q dot, which is you are using kat situ ada pakai meter and so on, then you have to standardize all the units. Okay, so next kita ada power transistors. Okay, it is mounted on a vertical aluminum plates and cooled by fan. So bila disebut cool by fan ni, kita dah tahu dia adalah convections. Of course, convections. Okay, and ask you to find what is the temperature of the aluminium plate. And then from this diagram, okay, it's given 15. 15 ni apa? This is actually 15 watt. That is the power for one transistor. Okay, so now because we have 4 transistors, so the total of our rate of heat transfer by convection here is 60 watt. Okay, 4 times with 15. And then the area, okay, in the question it didn't say any area. Actually in the question, I didn't change the question, sorry. So in the question it's supposed to give you the area, which is the area of the surface. Okay, so it is this value 0.22 times 0.22. Okay, this value is supposed to be in the questions. Okay, all right, so calculate for the area and then you get 0.0484. Okay, you know the area, you know the cube. Okay, and then you need to find the temperature, which is the surface temperature, this one. Okay, the T infinite is the room temperature. Okay, it is 25. Okay, so this area given, H also I didn't provide. Okay, so the H, because this is air, normally 25 watt per meter Celsius. Okay, so everything is known. You need to find this. Okay, rearrange the equation. So you get the surface temperature is 74.6 Celsius. Okay, so finish the first chapter. So any question so far? Any questions? Can you follow?
Belum ada lagi.
Okay. Am I too fast? Long intro, yes. Okay. So it's a long intro. It's actually the conductions, convections, and radiation is just the introductions. Okay, all that calculation is the introductions. That is the most basic knowledge that engineering student should know, should learn. Okay, but then after this, we're going to focus on the conduction itself. We're going to go deep inside the conductions. You have like more things that you're going to learn, and same goes for the convections. And we're not going to cover radiation chapter. Okay, up until convections and the radiation, conductions and convections. Okay, so any questions? No. So please record your attendance for today class in ULearn. Okay, the attendance will close at 10 a.m. You have another half an hour. So yeah, and next week, okay, please be on time. You have tests. Starts at 8:30 on the Friday. Okay, so in ULearn, all the table for the test provided in the ULearn as well. So please use that table. I don't want you to use other tables because the value might slightly change, slightly different. So when you do multiplications or divisions, okay, it will affect the value, the final value. So hint, all chapter in thermodynamics. Okay, so you only have 4 chapters. That is so basic chapters in thermodynamics. So the first one is like, it's just like introductions, the pressure. Okay, so make sure that you know how to calculate the pressure, the manometer pressure. Okay, the manometer concept. Okay, can you really understand how to check the fluid going up, going down, which is supposed to be positive and negative in the manometer? Okay, so take a look on that, and then you have also need to be able to read the tables. Okay, and What else? You have all the theories related to the first law. You have the polytropic, and then you have the isentropic, isotropic, whatsoever, isothermal, and everything. All the theories for the first law. So first law, you have the closed and open systems. So basically, that will cover theoretical parts for the first law of thermodynamics, and then and you have calculation as well. Please get ready with a piece of paper because you need to do calculations, and then scan it, or you can just simply take picture of your solution and post in the ULearn. Okay, you have calculations, you have multiple choice, fill in the blank, and yeah, that's kind of questions. All right. So ada satu je lah calculations, basically the manometer. Okay, so try to practice, make sure you really understand how to calculate the manometer. Okay, so normally I will not give any hint to my student, and then because I know you are electrical students and suddenly learn some things, okay, about more on the mechanical side, so I'm a bit lenient, okay. But if you did not perform well, okay, let's say you just get, your test is 20%, okay? It's a very big marks because your final only 30%. So your test will be 20%. Previously, your test only 10%. Okay, so it's 20%. So kena banyak sikit lah soalan dia. So good luck. Okay, do some revisions and everything. See you next week. Oh yeah, before we end the class, I want to show you the lab. Okay, so that next week, okay, you can straight away do the lab. Okay, so I'm going to share with you the screen again. And then, okay, so this is the lab. Okay, and this is the lab sheets heat transfer. And then next week, please do lab 1. Okay, conduction. So this is the lab sheets. Okay, so LO2, PO4 and everything. Okay, so the objective of this lab and the theories related, which is conduction. And then this is the procedures. You have this link. You can just click the link. Okay, and it will appear something like this. Okay, it's same with the convection and also radiations. So you have like this setup. Okay, you can just click on the show cross section so that you can see you have the fluids here, and then this is your plate in the middle. Okay, and then you have different materials. You have cardboard, glass, mica, asbestos, and ebonite. Okay, follow the instructions in the lab sheet so you can choose. If the question asks you to to use glass, then use glass. Okay, and then you can play around with the diameter. Okay, ranging from 10 cm up to 50 cm. Same goes with the thickness. Okay, and then the cold water temperature. You can play around. And then you have this, the GH and MH. Okay, you have to click this. Okay, the GH and MH, so that you get the voltage and the ampere values. So by knowing voltage and ampere, you can calculate for the power, which is equals to the rate of heat transfer. And then let's say I just like, okay, power on. So it runs. Okay, this is the time. Okay, and then you have like temperature until 8, I guess, the temperature. Okay, so until 20 minutes, it will stop. Then you can take your measurements. So this is temperature 1 value, and then you just click this. Okay, so this is the temperature 2 values, temperature 3, 4, up until temperature 8 values. So you have to record the temperature values. And then you can click the show result as well, so that it gives you the K value for this experiment for this material, which is 1.1 watt per meter Kelvin. Okay, so actually this unit kat sini, this temperature is not Kelvin, okay? This temperature is Celsius. Okay, so yang kat simulation ni, the temperature here, okay, this temperature here, okay, it is Celsius. Right, so bila dah buat, dapat dah how to run the experiment and everything. So you do the tables and then do the plotting, do the analysis, and then jawablah soalan-soalan yang ada dekat dalam lab sheet. So this is basically for the conductions. Okay. So the procedure is here. Okay, this is the analysis. What you have to do. Okay, you change the diameter and thickness. Fix the diameter and thickness, and then the water temperature also fix. And then using tuning, okay, you're going to fix the MH and GH. Okay, click on power and then record temperatures. Okay, and then repeat steps 1 to 5 for different materials. So for this case, okay, you have to discuss with your team members. Okay, what is the best? What is the thickness, diameter? What is the power that you want to use? Okay, the temperature is 15 Celsius. So, and then you're going to apply the same variables to different materials and compare. So you're going to plot to this, you're going to write down all your data that you collected, okay, in the simulations, and then write down what materials that are you going to use. Okay, that's how you do the experiment. So let's say for your group decides to use the ebonite solid. Okay, so your material ebonite solid. So for this case, okay, you vary the power, and then you see. Does it make any changes in the temperature and everything? And then and then you use the same materials. Okay, you change the thickness. And then the thermal conductivity. This is from the simulations, and then you have the thermal resistance. Okay, so the thermal resistance. Okay, you have to calculate. Okay, and then this thickness is remain the same, and then you just change the material. So this is what you have to do. Okay, and then answer the discussions, and then you see you have to plot graph. Please use Excel. Okay, no hand sketching, and then write 3 conclusions. Okay, so what you have to do, it's a 5%. Okay, uploaded your report in YouLearn 1 week after. So maknanya tu jatuh minggu raya lah. So upload lah dalam minggu tu. And then what pages that you should upload? Okay, this is the cover page. Okay, all groups, okay, must use this cover page. I don't want other than this. Okay, so write down all your team members. Okay, and from this page till the end page, okay, this is the only page that you need to upload in YouLearn. Tak payah page lab sheet kat atas tu, tak payah. Okay, don't have to. Sebab tu akan tambahkan size file. Okay. Alright, so that is the lab. Okay, and then next week, Tuesday and Wednesday at 10 a.m. Okay, you can do your lab, or if you want to do straight away right now, it's up to you. Okay, you can start with the lab, and then please make sure that you record your attendance. Okay, during the lab session next week. Clear, everybody? Group members still the same, yes, still the same. Following the thermodynamics team, the one that you registered in the YouLearn, so I will follow that. Okay, so any more questions? Okay, kalau tak ada, thank you everyone. Alright, so nak ucap selamat hari raya, it's still too early. Okay, So thank you everyone. Good luck for your test next week. Don't forget. Okay. So kalau terlupa without any reason, maksud saya reason yang kukuh, then there will no re-attempt test for you. Okay. Maknanya markah tak ada je lah. Okay. Alright. So next week, don't forget test and also lab. Okay. Alright. Bye everyone. Thank you.
Thank you,
Thank you,
Puan.
madam.
Thank you, madam.
Thank you, madam.
Bye, Puan.
Okay.
Selamat berbuka, madam. Bye.
Sama berbuka. Awalnya buka.
Time-time ni game plastik hitam beraksi, madam.
What?